Good morning, students. We have come to the end of this mathematical physics, which is on partial differential equations. We are going to discuss one-dimensional wave equation and one-dimensional heat flow equation, but in a different way. We are going to use method of separation of variables, and we are going to solve some problems on boundary conditions and initial conditions based on. And of course, in earlier classes, we discussed the one-dimensional wave equation and one-dimensional heat flow equation in an ordinary way. So now we are going to use the same two problems, but we are going to use only the method of separation of variables. And of course, we are going to use some problems. We are going to solve some problems based on boundary conditions and initial conditions. Separation of variables, it implies that there are more than two variables. For a single variable, we will be using only ordinary differential equation. If it is more than two variables, we will be using only partial differential equations. For example, just take the function. We just take the function which depends on here more than two variables, is three variables. And we are going to separate those variables in this basis. So we have f of x, y, comma t, which is equal to f1 of x, f2 of y, f3 of t. So we are going to separate all the variables. And we are going to differentiate this variable keeping these two as constant. We are going to differentiate this variable keeping these two are constant. We are going to differentiate this variable keeping these two are constant. So something like that. So the essence of this method is to separate the independent variables such as x, y, z, or here it is x, y, t, and which should be more than two variables. This can be done by assuming the original function exactly like this. And here f1 of x implies that it's a function of x only, and this is which is a function of y only, and this is function of t only. So f3 of t, which is a function of t only. This assumption has effectively separated the three independent variables in the original function f into the product of three separate functions. Each contains one of the three variables. See, one of the variables. The three separate functions f1, f2 and f3 will satisfy three individual ordinary differential equations involving separation constants. So it has to satisfy individual differentiation, satisfy ordinary individual differential equation. The solution of f1, f2 and f3 from these ordinary differential equations will result in the original function f, which is solution to the original partial differential equation. So what are the essence of separation of variables? A partial differential equation is two variables. For example, just take two variables. It implies that two ordinary differential equations. So we'll have two ordinary differential equations. Each involves one of the two variables. Suppose if you are going to have three variables, which implies that three ordinary differential equations which involves one of the three variables. Okay. So we have, suppose if there are two variables, we'll have two differential equations. If there are three variables, we'll have three differential equations. If there are four variables, then we'll have four differential equations. So now let us solve some problems using some boundary conditions. Using the separation of variables, solve du by dx equal to 4 du by dy, where u of, here it is x comma y, okay, because here u depends on x comma, there are two independent variables, x and y. U is a function. So in the problem, du by dx equal to 4 du by dy, it implies that u is a function of x and y. So there are two variables. U is a function. X and y are independent variables. Okay. So now u is a function of x comma y. So it implies that x equal to 0. So you have to substitute x equal to 0. So u 0 comma y equal to 3 e power minus 2y. So it is given. So we are going to solve this problem using separation of variables. So given that du by dx equal to 4 du by dy, which is equation 1, and let the solution be u of x comma y equal to x of x, y of y. So this is the method of separation of variables. So we are going to separate two variables because this function contains only two variables. So we are going to have x of x and y of y. The product of x of x and y of y is nothing but a complete solution. So we are going to assume this solution. Now you just differentiate equation 2 with respect to x. We are going to differentiate equation 2 with respect to x. keeping y as constant. So that means du by dx equal to y is constant. So you pull it out. You have to differentiate this function. So we have dx by x. Is it okay? I repeat. See here we are going to differentiate this equation with respect to x. That means y is constant. You can pull y out. So dx by dx, partial dx by dx. Now we have to differentiate this equation with respect to y now, and x must be a constant. So we have pulled x out. So this becomes dy by dy. This is capital Y, this is small y. Don't forget. Okay, y is a function of small y. Okay, it means y is a function. Y is a function of small y. Small y is independent variable. So now we have du by dx equal to this one and du by dy equal to this one. You can substitute in this equation. So we have substituted now. Very simple. Now just divide this one by xy and this side also by xy, capital XY. Divide both sides by capital X, capital Y. So that will give me this expression. yi will get cancelled. We have 1 by x dx by dx, which is equal to 4 by y. X will get cancelled. So we have 4 by y dy by dy. You just look at this expression, look at this equation, and it depends only on x. It depends only on y. If it is so, this must be equal to some constant. Like for example, in thermodynamics, we would have learnt PV equal to constant, correct? PV equal to constant. P1 V1 equal to P2 V2 equal to some constant. See, something like that. So we have it which depends only on x, this depends only on y. So this must be equal to some constant. So we have now separating these two, we have 1 by x dx by dx equal to k. So now I can take this dx this side, correct? So and x this side. So x, we have x here. So dx by x, which is equal to k dx. I repeat. See, I can take partial dx this side to right hand side. Remaining term let it be. So we have dx by x equal to k dx. Integrate on both sides. Integrating, that will give you log x. Okay, log x, which is equal to kx plus c1. Okay, log x equal to kx plus c1. Is it okay? So you are going to integrate this one. It gives you log x, and this must be kx. Integration constant is c1. We will keep it this c1. And raising to the power on both sides by exponential e. Just raise on both sides with e. So e and log will cancel. We have x of x equal to e to the power kx plus c1. So this is the solution of x. Similarly, you can solve for y. So 4 by y dy by dy equal to k. So we have now, as usual, the same technique. You bring this dy to right hand side. So that will give us dy by y, which is equal to k by 4. So 4, you just bring 4 to the right hand side. So k by 4 dy. Integrate, that will give you log y, which is equal to k by 4 is constant. So you have y plus some constant, integration constant, which is nothing but c2. As usual, just raise to the power exponential on both sides. So that will give you y of y, which is equal to e to the power k by 4 y plus c2. So now we have solved x of x and y of y. We have solved x and y. We can substitute here. Get the complete solution. Simple. So we have solved x and y. So substituting in this equation, we have u, which is a function of x comma y, small x y, which is equal to x and y, which is equal to, we have already obtained the results of x, obtained the results for y. You just substitute here. And this can be simplified as e to the power kx plus k by 4y and e to the power c1 plus c2. c1 plus c2 both are constant. If we add, we can obtain another constant. We are going to raise e to the power, that also will become a constant. Okay, c1 is a constant, c2 is a constant. If we add these constants, we will get another constant. E to the power c1 plus c2, we will have another constant. I am going to keep this as a. So a is nothing but e to the power c1 plus c2, which is a constant. Now substitute in this expression. We have u of x comma y, which is equal to a times e to the power kx plus k by 4 y. So this is the complete solution of this equation. So this is equation. Okay, now we will have to use this one. So boundary conditions given as u of 0 comma y. Instead of x, we will have to substitute 0. Okay. Now given that e of 0 comma y equal to 3e to the power minus 2y. Now we have to use equation 9. So this is equation 9. So we have e of 0 comma y equal to a e to the power, wherever you find x, you substitute 0. So e to the power 0 plus k by 4y, which is nothing but a e to the power k by 4y. And what is given here? 3e to the power minus 2y. So this is nothing but your 3e to the power minus 2y. Okay. Now I can compare both sides. Comparing both sides, a will give me 3 and k by 4 is nothing but minus 2. So a equal to 3, k by 4 equal to minus 2, so k equals minus 8. So now I have found out the value of k and I have found out the value of a and k. You substitute in this expression, we will have a complete solution. So u equal to 3e to the power minus k is nothing but minus k. So k is nothing but minus 8. So minus 8x plus k by 4 minus 8 by 4 y minus 8 by 4 is nothing but minus 2. So we have 3e to the power minus 8x minus 2y. So this is our complete solution. So e of x comma y equal to, without a constant, see earlier there was a constant a, now we have solved for a. So 3e to the power minus, I pulled minus sign out, so minus 8x plus 2y. So this is the solution using separation of variable. Very simple technique, we will have to separate the variable and solve it. Now we are going to have some discussion on one-dimensional wave equation. So this is our one-dimensional wave equation. Okay. See, on both sides we have partial differential equation with 2 degrees. See, here we have, so second order differential equation on both sides. U depends on x and t. There are two independent variables, x is here and t. So there are two independent variables, x and t. U is a function. U is a function of x comma t. So this is one-dimensional wave equation because x alone is that. See, it can go only through x direction. So that's why one-dimensional wave equation. So d squared u by dt squared equal to c squared times d squared u by dx squared. So this is one-dimensional wave equation. And the solution, as usual, the same method we are going to use. The solution that of this equation using method of separation of variables is given by this. The same method. U of x comma t, see, u of x comma t, which is equal to x and t, x of x, t of t. Now differentiate with respect to x, we will have this one. Differentiate with respect to 2, we will have this one. Okay, so easy. So keeping this t as constant, we will have to keep, we have to differentiate with respect to t here. So du by dt, which is equal to x dt by dt. X is constant. Now here we are going to differentiate with respect to x. So keeping t as constant. So du by dx equal to t times dx by dx. Now it's given that second order differential equation. So we'll have to differentiate again. So that will give us d squared u by dt squared equal to x times d squared t by dt squared. Here it is d squared u by dx squared equal to t times d squared x by dx squared. You substitute for d squared u by dt squared expression. You substitute for d squared u by dx squared expression here. So we will have this. Just a substitute. See here we have d squared u by dt squared is given by x times d squared t by dt squared. So x times d squared t by dt squared, which is equal to c squared as it is, and instead of this you have to write this t times d squared x by dx squared. So look at this equation. And one more look at this equation first. I can bring this x this side, I can bring this t this side. So if I bring this one, then x alone one side, t alone will be on the other side. So we have separated the variables. So that's the idea. So same equation. I have brought this one c squared t times this side. So that will give us 1 by c squared times t times d squared t by dt squared, which is equal to, I have brought this x to that side, thus that will give me 1 by x d squared x by dx squared. As usual, we have separated the variables. So this belongs to only t and this has only x, and which is equal to lambda, some constant. So last time we kept as k. So this time we are going to keep it as lambda. You can keep it as any constant. Now there are three cases. One is lambda equal to 0. So lambda can be 0. one case. Another case will be lambda can be a positive value, greater than 0. Another case will be lambda should be a negative value, so less than 0. So there are three cases. Suppose if lambda equal to 0. If lambda equal to 0, this is equal to 0 or this is equal to 0. So we have now, if lambda equal to 0, it implies that d square t by dt squared equal to 0. The solution of this differential equation is nothing but this. We have already stated earlier. You just integrate with respect to t. Integrate this with respect to t will give you dt by dt, d capital T divided by d small t, which is equal to some constant c1. Again you integrate, that will give you t, which is equal to c1t plus c2. I have written c1 plus c2t. Okay. So if you are going to integrate 2 times, you will get this answer. Similarly, if you are going to integrate 2 times, you will get this answer. Okay. So now we know that the separation of variable e of x comma t equal to x of x t of t. We have found out now x. We have found out now x. We have found out now t. You just multiply these two. Product of these two, that will give us the complete solution. That's the idea for the first case, lambda equal to 0. Simple. So we have now e of x comma t, the solution of x and solution of y, the product solution of t. The product of these two will give us the complete solution for the case lambda equal to 0. And for lambda is positive value. If lambda is positive value, for example, we just say k squared, and this equation becomes. So this is the original equation. Lambda equals positive value. Positive value means k squared. So d square t by dt squared equal to, instead of lambda you substitute k squared. So k squared c squared t. Similarly on this side we have d squared x by dx squared equal to k squared x. It's okay, k squared x. You bring this k that side. So k squared x. The solution of this is nothing but this. The solution of this one will be this. Okay. So you have to integrate 2 times, you will get the solution of t. You will have to integrate 2 times, you will get the solution of x. Okay. And we know the product of these two will give you complete solution. Is it okay? I repeat, the solution of, you have to integrate 2 times, you will get the solution as t of t. You will have to integrate 2 times, you will get the solution of x of x. Product of these two will give you complete solution. Suppose if k is lambda is negative, lambda is less than 0, then we are going to keep it as this as minus k squared. So in that case we are going to substitute, instead of lambda you have to substitute minus k squared. So you will have minus k squared c squared t. Okay, and here also you have minus k squared x. Now this can be kept as a d squared. I can bring this term to left hand side, so that will give me this. Similarly here also I can keep this as d squared, 2 times differentiation with respect to x. I am going to bring this term to this side, so that will give me plus k squared x equal to 0. Is it okay? Now, so this equation is second order differential equation, partial differential equation. So the auxiliary equation is nothing but m squared plus k squared equal to 0, and m equals plus or minus ik. And here it is m squared plus k squared c squared, so m equal to plus or minus ikc. Okay, the solution of this is auxiliary equation we have already studied earlier. So the solution of this will be, and this, the solution of this will be this. Your t of t will give you this, the solution of this, and solution of this differential equation nothing but this. The product of these two will give you complete solution. So which is nothing but this. Okay, so c9, which is a constant, so cos kx plus c10, again it's a constant, sin kx, this is a solution of x of x, and this is a solution of t of t. Product of these two will give you complete solution. So that's the idea. Okay, so now we will solve some other problem. The one-dimensional wave equation is given by this. Now we are going to use some boundary conditions and initial conditions. Earlier we have not used, we have solved. So we have solved some one-dimensional wave equation, and this problem goes like this. We are going to have some boundary conditions, and we are going to have some initial conditions also. Okay, so this is the same one-dimensional wave equation, but we are going to use these two conditions, boundary conditions and initial conditions. and this is one dimensional wave equation. Boundary conditions given as u is a function of x comma t, so it is 0 comma t. So wherever you find x, you have to substitute 0. So 0 comma t, which is equal to 0. So this is boundary conditions have been given in the problem itself. And u of L comma t, you just consider this is a one dimensional wave equation, and initial is x equal to 0 and this is x equal to L, and which is a function of u of x comma t. Okay, the length of the string is nothing but your L. So this is one dimensional string, length of the string is nothing but your L. So initial conditions are given. See here, u of 0 comma t equal to 0, u of L comma t also is equal to 0. So boundary conditions are given in the problem. U of 0 comma t equal to 0, u of L comma t equal to 0, your x becomes L. So this is your x, one dimensional wave equation, and x is nothing but your L. So u of L comma t equal to 0. So both the boundary conditions are given here. And what are the initial conditions? Initial conditions are given here. U of x comma 0, when t equal to 0, f of x. Here when t equal to 0, du by dt equal to 0. So we will have to use both boundary conditions and initial conditions to solve one dimensional wave equation. So let us solve. The solution of one dimensional wave equation is obtained by using separation of variable, which is given by this. Okay, u is a function of x comma t equal to x of x and t of t. And as usual, we will have to differentiate two times with respect to t. We will have this one. We will have to differentiate this with respect to x. You have this one. So instead of this, you will have to substitute this. Instead of this, you will have to substitute this in equation 1. So we have now this. I repeat. See here, you will have to differentiate this separation of variable, that solution, two times with respect to t. We have this. We have if you are going to differentiate two times with respect to x, we will have this. Okay. Now product of these two, I repeat, d squared u by dt squared is given by this, d squared u by dx squared is given by this. So you can substitute in this equation 1. So we have this. Now I can bring this c squared t to left hand side, I can bring this x to the right hand side. So we have this. And of course this belongs to t and this belongs to x, which can be equated to some constant lambda. So we have kept exactly like this. And as usual, we have three cases, like in the last video lecture we discussed. So lambda equal to 0 is one case, lambda equals minus value is another case, lambda equal to plus value will be another value. So first one, lambda equal to 0, that will give you d squared x by dx squared equal to 0, d squared t by dt squared equal to 0. The solution. How to find out the solution? As I told you earlier, we will have to differentiate. We will have to integrate two times. Integrating two times. First we will integrate only once. We have dx by dx, which is equal to c1, some constant. We will have to integrate only once, that will give us dt by dt equal to c3, some constant. Integrating again, we will have to integrate. Okay, so what I have done is, I am going to take this dx to this side. So we have dx equal to c1 times dx. So this one, integrating on both sides will give you x of x, which is equal to c1 times x plus integration constant is nothing but c2. So c1x plus c2. Similarly, we have t of t, which is equal to c3 times t plus integration constant is nothing but c4. So this is your complete solution, x of x and t of t. Okay, the product of these two will give you a total solution, u of x comma t, which is equal to x of x, t of t. You substitute for x of x, you substitute for t of t, so that will give you complete solution, equation 6. Now lambda can be a positive value. If lambda is positive value, then lambda equals k squared. You can keep it as k squared. So as usual, d squared t by dt squared equal to k squared c squared t, d squared x by dx squared equal to k squared x. You bring this term to left hand side, you bring this term to left hand side. So that will give us this. You can pull x out, you can pull t out. So corresponding auxiliary equation is nothing but this, d squared minus k squared equal to 0, d squared minus c squared k squared equal to 0. The solution will be m equal to plus or minus ik. Here the solution will be plus or minus ck. Plus or minus k. Here it is plus or minus ck. What is your complementary function? So complementary function is nothing but you have a solution. You have to have a solution. So your complementary function will be c5 times e to the power kx plus c6 times e power minus kx. Your particular integral is 0 here. Total solution will be particular integral plus complementary function, which we have already studied earlier. But here there is no particular integral. If there is some constant on the right hand side, then we will have particular integral. So there is no constant here right hand side, which is equal to 0. See here, which is equal to 0. If there is some constant, then we can say the particular integral is not 0. Okay. If it is 0, particular integral is 0. If some other constant exists, particular integral will exist. So particular integral is 0 in this case. So total solution will be complementary function plus particular integral. So your PI is 0. So total solution will be x of x equal to this alone, complementary function alone. So now we will go for t. So our complementary function is given by this, and as such there is no particular integral. So the total solution will be complementary function itself. So product of these two will give a complete solution as usual. So now lambda is negative value. So we have lambda equal to k squared, and this becomes positive value. Correct? Here it is minus. So if we are going to bring this term to this side, so that will give us plus. So this is plus and this is plus. Okay. Now as usual, your auxiliary equation is nothing but d squared plus k squared equal to 0. Your d squared, I can bring this k squared to that side, that will give us minus k squared. Minus 1 can be written as, your minus 1 can be written as I squared. So I squared k squared, your d will be plus or minus ik. And here d squared will be minus c squared k squared, and instead of minus 1 we can write I squared. So I squared c squared k squared. So d will be plus or minus ick. Here d will be plus or minus ik. Okay. The solution can be obtained as exactly like this. So we have some constant cos kx plus c10 some constant sin kx. Similarly here we have c11 cos kct plus c12 sin kct. And of course particular integral 0. Here also we have particular integral 0. So we will have to add these two, we will get a complete solution. So we have a complete solution. X of x is given by this and t of t is given by this. The product of these two will give us the complete solution for the third case. Lambda is negative. Okay, so u x comma t is given by the product of these two. So this is your complete solution. Okay, now initial and boundary conditions are given in the problem. So boundary conditions are given in the problem as u of x comma t. So 0 comma t, wherever you find x, you will have to substitute 0. Wherever you find x, here you will have to substitute L. L is the length of the string. Okay. So now taking the first condition. So first we will go for the first condition. This is for the second condition. Okay. So first we are going to use x equal to 0. See, x equal to 0. Using equation 8, in equation 8 and using equation 9. So now this is equation 9. So this is equation 8. You substitute x equal to 0 here. This is equation 8. This is equation 9. Okay. Now substitute x equal to 0 in equation 8. X equal to 0 will give you cos 0 is 1. So C9. Sin 0 is 0. So we have C9. Okay. Here it is t. We can't substitute. T as such it is t. For x alone you have to substitute 0. Okay, don't forget. So we have now C9 times C11 cos kct plus C12 sin kct. This side is given. So that's why we put as 0. I repeat. See, u of 0 comma t equal to 0. So that's why I have kept 0 here. Instead of this I have substituted in equation 8 and I have obtained this. Any doubt? So it implies that C9 can be 0 or this term can be 0. Correct? If phi x equal to 0, it implies that phi should be equal to 0 or x should be equal to 0. Phi cannot be equal to 0. Only x alone can be equal to 0 for any trivial solution. So we have C9 equal to 0. This term must be equal to 0. This term cannot be equal to 0. If it is equal to 0, that's all. Only possibility is C9 equal to 0. So if C9 equal to 0, you substitute in equation 8, that will give you, if C9 equal to 0, that will give you, this term will go up, you have this term alone. So u of x comma t equal to this one. So this is equation 11. I repeat, see here, we have C9 equal to 0, we have obtained. After substituting first boundary conditions, we have obtained C9 equal to 0. You substitute here. Instead of C9, you have to substitute 0. So this term will go up. This term alone will be there. So this term alone is there. Is it okay? And this term, let it be like this. You have x comma t is given by this. Okay, now we will have to use second boundary condition. Second boundary condition is given as x equal to L, and of course u comma L comma t, u of L comma t equal to 0. So wherever you find x, you have to substitute L. So wherever you find x, you have to substitute L. So we have now C10 sin KL, C11 cos KCT plus C12 sin KCT. This is equal to 0. Only possibility is C10 sin KL equal to 0. Okay. So C10 sin KL equal to 0, it implies that C10 cannot be equal to 0, sin KL should be equal to 0. If sin KL equal to 0, the condition goes like this, sin KL equal to sin n pi. Sin n pi is 0. Sin n pi, sin 1 pi, sin 2 pi, sin 3 pi, so sin n pi is 0. So sin n pi equal to sin KL, and we have KL equal to n pi. So wherever you find K, you can substitute n by pi. N pi by L. N belongs to positive integer. Okay, is it okay? K equals n pi by L. So equation 11 becomes C10 equation 11. So this is 11. It becomes wherever you find K, you can substitute by n pi by L. So C10 sin n pi x by L, C11 cos, instead of K you have to substitute n pi by L. So n pi by L times Ct plus C12 sin n pi Ct by L. Now you just multiply this one and this one. This gives me C10 and C11. So C10 and C11 I can keep it as An. This is a constant, this is a constant, An is another constant. So C10 multiplied by C12, that will give me Bn. So instead of this equation I can simplify and write summation over, because n is here, n is a positive integer. So 1 to infinity, summation over n equals 1 to infinity An cos n pi Ct, C cos n pi Ct by L plus Bn sin n pi Ct by L times sin n pi x by L. So this is our complete solution. Is it okay? Now we have used only boundary conditions. Now this is initial conditions. Initial conditions are given in the problem itself. V of x comma 0 equal to f of x and du by dt equal to 0 when t equal to 0. So there are two boundary conditions and two initial conditions are given in the problem. You have to use and solve, try to solve. Putting now t equal to 0, it implies that x comma t. So t equal to 0 in equation 12. So this is equation 12. Put t equal to 0 here. So this is equation 12. Putting t equal to 0, that will give me cos 0 is 1. So we have an alone. Sin 0 is 0. This one will go up. This multiplied by this will give me solution. So this is f of x, which is equal to u of x comma 0, which is equal to summation over n equal to 1 to infinity an sin n pi x by L. Okay. Now it is given us another boundary condition is du by dt equal to 0. So we will have to differentiate once with respect to t, and this one should be equated to 0, and we will have to substitute t equal to 0, that condition. So differentiating this. So differentiating equation 12. So this is equation 12. We will have to differentiate with respect to t only once. So that will give me du by dt. So we will have to differentiate. Differentiating, that will give me, here n pi c by L is constant. So you can pull it out. Here also n pi c by L is constant. You can pull it out. Correct? So I have pulled out n pi c by L. When I am going to differentiate, that will give me, this one will give me minus an sin n pi ct by L times n pi c by L. I have pulled n pi c by L out. So that will give me minus, differentiating cos will give me minus sign, differentiating sign will give me cos. And here as it is written, because it doesn't contain t. See here only we have x, variable x. We have differentiated only t. So as such we will have to write. Is it okay? Now substitute t equal to 0. Substituting t equal to 0, so this will give me 0 and this will go up with 1. So we have bn alone and this will be as it is. So we have now 0 which is equal to bn, okay, we have bn n pi c by l, okay, sin n pi x by l. So this is equal to 0. So now it implies that bn equal to 0 or this term should be equal to 0. So bn equal to 0 for all values of n. So we have now using bn equal to 0 in equation 12. So this is equation 12. So bn equal to 0 means it will go off. So we have this term and this term alone. We have these two terms alone. So this is your complete solution of one-dimensional wave equation using boundary conditions and initial conditions. So this is the answer. And your an is nothing but given by this expression. So this is the answer. So this is your complete solution. We have used two boundary conditions and two initial conditions. We have obtained this, the solution. U is a function of x comma t, where your an is given by this. Okay. So now let us we'll stop today.